In this video, we'll be looking at the inverse tangent function. Just like we did in the previous two videos with sine and cosine, we're going to go ahead and focus on originally the function tangent of x. Now, for the tangent function, it's quite different than that of the sine and cosine function in that it's cyclical with asymptotes. So if we remember very carefully that the tangent function originally starts here, has a value of importance there, has an asymptote next, value of importance, and then another 0 here. This being one cycle of the tangent function, it cycles up this way, it cycles down this way, with this location being a value of 1, negative, and this point right here being a value of 1. So one more time, in terms of sine and cosine, we were very particular about picking a section of values so that those functions' inverses were continuous. We're going to do the same thing for tangent. It's important for us to recall that the tangent function actually continues going this way with another asymptote here. If we recall, the period of tangent is pi, so this location is pi over 2, which makes this location right here a negative pi over 2. Because there should be another point right here where it intersects there, being that negative 1 value. So if we look at this carefully, it should be relatively easy for us to select an obvious continuous set of values, and it should actually quite compare to that of the sine inverse functions. So in this case, we're going to limit the tangent function to be between negative pi over 2 and pi over 2. The actual same set of values that we limited the sine inverse function to be. So if I select this domain only for the tangent function, then I can pick the inverse tangent function, f inverse of x equals to, again, arctan is one way that we could write it, or tan inverse is another way we can write it. The domain of values that we're allowed to pick in this function, you'll notice here very carefully that the y values for this function are all real numbers. This will encompass every single possible y value. So that means that the domain of the inverse tangent function is actually all real numbers, very much like that of the other functions we refer to. Sorry, those don't need to be there. So the range of values then is going to be actually the domain of the original function. Again, recall that we swap all the x's and the y's. So the values that we're allowed to get back, or the values that we're allowed to pick when evaluating an inverse tangent function, is the same set of values that we picked for sine. So in this case, we can talk about, again, the way that we would evaluate a specific tangent function. Before I get into that, let's go ahead and take a look at this graph real quick. It should be relatively simple based on the way we've got this set up. Again, keep in mind that we're just simply reflecting this set of values over the xy axis. So instead of it looking like this, it's going to be sideways. So we're going to be very careful. Notice that all this stuff here is in the positive x and y quadrant. So we're going to go ahead and put that exact same set of values in the x and y quadrant. This is going to look something like this if we do it really careful and really accurately to the best of our ability. And then it'll do the same thing over here, but it'll be flipped. So it'll do something like this. This should actually look quite very much like, and I kind of exaggerated this side, but not the other side. It should look quite like a cube root function, given that this thing looks kind of like a cubic function if we ignored that it was cyclical altogether. Keep in mind it's not, because it has those asymptotes. One at the value up here of positive pi over 2, and one down here at the value of negative pi over 2. We do have some, again, nice important points here. One right there, one right there. Such that this is 1, this is negative 1, and that location is there, and that location is there. It's not terribly important that those points are in there anymore. You'll notice now that the domain for tangent inverse is it can take in any possible value, but it will only spit back values between negative pi over 2 and pi over 2. So this next example of values that we're going to talk about, again, our goal is to pick an angle measure. Again, this part is not part of the question. The question is, for what tangent inverse of radical 3? What is tangent inverse of radical 3? Well, I'm going to remember that every tangent inverse is equal to some form of an angle. I'm also going to go ahead and rewrite it as the tangent of theta equals to radical 3. I just need to figure out what that angle is. Then I'm also going to recall that the little notations I've been making on a unit circle form, or at least a quadrant form, is that this set of values is where sine is defined. This set of values is where cosine is defined for the inverse functions in particular, and now tangent follows the same set of values for sine. So you have tangent and sine here for first quadrant and fourth quadrant, and then for first and second quadrant, you're going to have cosine inverse, its values defined. So I just need to figure out a location where the tangent of theta is equal to radical 3. Well, I know I have 1, 2, 3 points here, and I have 1, 2, 3 points here. I know that if this value was a value on the unit circle, which I do know that it is, if we can't recall that, then we should check all of the possible values here. Why shouldn't we have to check these ones? Well, because these values should be the values that turn out to be negative. Again, you'll notice that this is going to be a positive x but a negative y, and tangent is, in this case, sine over cosine, so y over x in the unit circle. So all the values down here will be negative, so I'm just going to focus on these three locations up here. If we recall, I'm going to have 1, 0, 0, 1. This is going to be radical 3 over 2, 1/2. This is going to be radical 2 over 2, radical 2 over 2, and this is going to be 1/2, radical 3 over 2. The reason why I'm ignoring this middle location here is because that's going to be 1. Tangent of theta is going to be equal to 1 there. Radical 2 over 2 divided by radical 2 over 2 is going to be 1. So I don't need to focus on that one. I did that one in my head. I'm going to look at these two here, and I'm going to ask myself, well, which one of those makes the most sense? Well, the tangent of theta equals to radical 3 over 2. If I start with this location, I'm going to test this location, meaning I'm going to put the y value divided by the x value. I'm going to go ahead and flip change that information, so it's 1/2 times 2 over radical 3. The 2's are going to cancel out. I'm going to have 1 over radical 3, which if I rationalize that denominator, which we should always do, that is not the same thing as that. So now we can go ahead and say, well, it's probably going to be this location, this point right here. But it's possible that it won't be. Okay? And if it's not going to be this location, then chances are this is going to be more of a calculator problem than anything else. But in this particular situation, I did set it up so that we're going to talk about non-calculator issues first, and we should be checking all these for unit circle values first and foremost. So I'll have radical 3 over 2 divided by 1/2, which is the same thing as multiplied by 2 over 1, which is the same thing as radical 3. And therefore, it's this location that we're referring to, and that location there then is simply pi over 3. So I know that this inverse tangent function, theta in this case, which is equal to tangent inverse of radical 3, is actually equal to pi over 3. So that's that kind of example for tangent. Another type of example you might have is, say, tangent inverse of -1. For this one here, we'll notice we'll be focusing on this point right here because it's actually relatively simple to find tangent inverse of 1 or -1, given that it's radical 2 over 2 divided by radical 2 over 2 is 1. So this is the location we're playing with. Be very, very specific about how you define this. Remember, tangent inverse will only spit values back between negative pi over 2 and pi over 2. And therefore, that location there is not technically 1, 2, 3, 4, 5, 6, 7 pi over 4, but negative pi over 4. And that's how you evaluate the tangent inverse functions. Again, if in some cases you might find some of these values that don't actually evaluate smoothly. In that case, say the example is tangent inverse of -9.65. This value is obviously not on the unit circle. It's a value that we can't just simply go ahead and say, oh yeah, I remember that from the unit circle. So we're going to have to utilize our calculator to actually evaluate that number. In order to do so, you're going to go ahead and in your calculator you should have buttons that have the inverse, tan inverse, cosine inverse, sine inverse, and all you'll do is you'll go ahead and plug that in, and you'll plug the number, in this case -9.65, into that. You'll hit enter, and it will give you back a number. Now keep in mind that this number is going to come back in two possible different ways. Every inverse trig function is an angle. So either it's going to spit back a degree measure, and you'll notice down here in my calculator it tells me that this is in degrees automatically, or it's going to spit it back in radian. So be very, very particular about how you write your answer. In most cases for the inverse trig functions, in terms of these answers, for it to make the most sense, we will probably ask for you to answer these types of questions to round to the nearest degree. And again, notice also that it's still spitting back a negative angle degree measure, and also notice that it's still between, technically, 90, negative 90, and 90 degrees. That value does make sense in the range of values that the inverse tangent function has defined. You might see values like this in terms of sine and cosine, but just recall that for those ones, you're simply going to go ahead and do the same concept, is plugging them into the calculator, getting back a measure, be it degrees or radians, depending on how the question specifically asked.